Today we are starting our last unit on sequences and series. Your test for this unit is Tuesday, May 17th. And just as a reminder, the final exam will not be cumulative over the whole semester. It'll just cover the last 3 units. So final exam will cover sequences and series, conics, and matrices. But the test for this unit is Tuesday, May 17th. Today we're going to be talking about arithmetic sequences, how to write their equations, how to find future terms in an arithmetic sequence, what an arithmetic sequence even is, and it's kind of a weird word because it looks like the word arithmetic, but you actually say arithmetic. So, um, yeah, I don't think I have to say anything else about that. Let's move along to the notes. First of all, a sequence, just any sequence, is just a set of numbers with a pattern. So this first guy up here is a sequence because the same thing is happening, or like there's a pattern to the set of numbers. So like from 1 to 4 to 7 to 10 to 13, we can notice a pattern and continue it because they are just adding 3. The next one, they're not adding the same number every time, but they are multiplying by the same number each time. So we could continue that on by multiplying by -3, 162, and -486. And the pattern would be multiplying by -3 each time. Take a look at the last one and see if you can figure out what the pattern is there. In this one, they're taking the 2 previous terms, adding them together to get to that next term. 1 plus 2 gives you 3. 2 plus 3 gives you 5. 3 plus 5 gives you 8. So to get to this next one, we would add 13 and 21 to get 34. Then we would add 21 and 34 to get to 55. So they're adding the 2 previous terms. These are all examples of sequences because it's a list of numbers that has a pattern. Today, we're going to be talking about a specific type of sequence, which is an arithmetic sequence. An arithmetic sequence is a sequence or a pattern where the same number, and I want you to like all caps or underline or highlight the word same because that's important. The same number is either added or subtracted each time. So in our previous examples up above, the only one that was arithmetic was example number 1, because they're adding 3 each time. The number that is added or subtracted each time is called the common difference, and we use the lowercase d to refer to it. So if you see a lowercase d in an equation, that is referencing the common difference. So in these next 2 examples, take a moment and try to figure out what the pattern is and what the common difference would be. The first one, they're adding 2 each time, so the common difference is 2. And the next one, they're subtracting 3 each time, so the common difference would be -3. It's helpful to like summarize an arithmetic sequence with a formula so that you can find future terms in the sequence if needed. And you can write a formula in one of 2 ways. You can write it with a recursive formula, or you can write it with the explicit formula. On the rest of this page, we're going to be talking about the recursive formula. And I'm just going to put a little sad face next to this one because this one is not as helpful as the explicit formula. The explicit formula is much more user-friendly in terms of finding future terms in a sequence. But you have to know both, so here we go. We're rocking and rolling. Recursive formula has 2 pieces. You first state what the first term is. I'll go over this notation in a second, but A1 is your first term. So you first state what your first term is. Then, to find a future term in the sequence, A sub n, you take the term before that one, A sub n minus 1, and you add the common difference. Now, when you actually write the recursive rule, you're only plugging in two things. You're plugging in what the first term is, and you're plugging in what the common difference is. All those other things will stay like A1, A sub n minus 1. And we'll practice writing the recursive rule in a second. But just so you know for future, like for what this is referring to, what these variables are, n, whenever you see the letter n, it's referencing the term number. So if I say find n, like find the value when n equals 7, it's asking you to find the 7th term. A sub n is the nth term. So for example, a with a little 5 down here is the 5th term. A sub n minus 1 is the previous term. All right, let's look at this first example, and we're going to write the recursive rule for the following sequence. First thing you would need to do is take a look at that example and figure out what is happening each time. Find out if it's even arithmetic. In order to be arithmetic, the same number has to be added or subtracted. So if they like subtracted 2, and then subtracted 1, it would no longer be arithmetic. You have to subtract the same or add the same each time. So this one, they are adding 2 each time. So our common difference, which would be helpful to make note of, is 2. If we're actually going to write the recursive rule, you start out and you say the first term is, and you fill in the blank. So our first term is where the sequence starts. So we'd say the first term is 24. That's part 1 of the recursive rule. Then, to find any future term, a sub n, so any future term in the sequence, you take the term before it and you add the common difference. So for example, this would be like, if you want to find the 25th term, you would take the 24th term and add 2 to it. It's not very helpful because it doesn't save you any time. Like if I want to find the 100th term, I'm still going to have to go all the way to the 99th term to find the 100th. Take a moment and try to write the recursive rule for this guy. Write the recursive rule for that scenario. If you're having a hard time finding the common difference, you can always take the second term and subtract the first term. So if this was hard for you to see, you could have done the second term, negative 18, minus 3 to get negative 21 is our common difference. That'll work every single time. If you want to write the recursive rule, you should have started out by saying that the first term is 3, and then to find any future term in the sequence, you take the term before it and you plug in the common difference, which is minus 21. And the next ones, we're going to use the recursive rule to find the 5th term. So in each of these, we're simply finding the 5th term. We're given what the first term is. So we're starting at 3. We're also given what the common difference is. Add 4. So if we have 3 and add 4 to it, we would get 7. Add 4 to it, we would get 11. Add 4 to it, we would get 15. Add 4 to it, we would get the 5th term is 19. Use that same skill on the next guy. Figure out what the first term is, then use the common difference to find future terms. Should start at negative 2. That's our first term. The common difference is negative 6, so we're subtracting 6 each time. So you should have had negative 8, negative 14, negative 20, and finally we get to the 5th term, which is negative 26. That's how you'd use the recursive rule. Not a big time saver. It's a nice way to like explain a sequence with a formula, but it doesn't really save you any time. The big mamma jamba good guy is the explicit formula. So I want everyone to go by the explicit formula and draw a big old smiley face. Maybe he has his thumb up, because this is the one you want to use. The explicit formula looks like this. It's only one formula. It says to find a future term in the sequence, you take the first term and add the common difference times the term number that you're looking for minus 1. So this is our first term. This is the common difference. This is a term number. And this is the future term value. So let's see how it works. We've got an arithmetic sequence here. At least we think it's arithmetic. Let's check it. 7 to 12 is plus 5. 12 plus 7 is plus 5. 17 to 22, add 5. Add 5. So our common difference is 5. Always helpful to find that first. We're going to do a little bit of review and write the recursive formula. So the recursive formula would say first term is 7. To find any future term, a sub n, you take the term before that one and you add the common difference. So again, remember that you're just plugging in first term and common difference. To write the explicit formula, the more helpful one, oh, by the way, up here when you're actually plugging in for the explicit rule, you typically only plug in A1 and your common difference to write your base explicit formula. Now, like as you use it, you'll plug in different things, but if you're asked to write the explicit rule, those are the only two things you have to plug in. So for this one, we would say any future term can be found by taking the first term, 7, adding the common difference times the quantity of whatever term number you're looking for minus 1. We can then use that to find, in this next example, the 30th term in the sequence. Again, we will not use the recursive rule for this because you'd have to list out 30 different numbers. Instead, we are going to use the explicit rule, which saves us a lot of time. The main thing you need to recognize is that they're asking you to find the 30th term. So they're telling us that our term number, our n value, is 30. So A, with a little 30 by it, the value at the 30th location is 7 plus 5 times 30 minus 1. I would encourage you to just plug that smack dab into your calculator. If you're going to do it like in multiple steps, remember to do parentheses first, then multiply, and then add the 7. Don't do 7 plus 5 and then multiply by 29. That's not following the order of operations. To save yourself the errors, plug it into your calculator, and you should get that the 30th term is 152. That saves you a lot of time compared to the recursive rule where you'd have to just list out 30 different terms. The next one, be careful here. They're saying at which term number, so in other words, what is n going to be when it went, like at which term number will the pattern reach 467? This 467 here is not asking us for the 467th spot. It's saying when will it get to 467? So they're giving you a sub n. They're giving you a term value. So you'll still use the explicit rule. So we'll use this guy up here. But now we know a sub n, and we don't know n. So your equation is going to look something like this. 467 equals 7 plus 5 times n minus 1. And you're solving for n. You're trying to find out at what term number that value is going to occur. If I was going to solve this, I would go ahead and subtract 7, get 460 equals 5 times n minus 1. Then I would divide by 5. 460 divided by 5 is 92. So we get 92 equals n minus 1. So n would equal 93. So that would occur at the 93rd term. By the way, back up here, when you solve this equation, if you prefer to distribute and then combine like terms and then move, like solve for n, that's also completely fine. There's multiple ways to solve that equation. Whatever you do, don't add 7 and 5 first, because that 5 is being multiplied by all of the n minus 1 before it's ever being added to 7. Take a moment, take a look at this next pattern right here, and see if you can find the common difference. Remember, if you ever struggle to find what the common difference is, you can always take the second term and subtract the first term. So in this case, 53 minus 95. And it doesn't have to be the second minus the first. It can be any new term minus the term right in front of it. So if we do 53 minus 95, you would find that your common difference is negative 42. So they're subtracting 42 each time. Take a moment and write the recursive rule. Write the recursive formula for that sequence. You should have plugged in that your first term is 95. To find any future term, you take the term before it and subtract your common difference of 42. Now take a moment and try to write the explicit rule. You should get a sub n equals your first term, 95, minus 42 times n minus 1. If we want to find the 30th term in that sequence, they're giving us n equals 30, so we plug that in right there. Go ahead and take a shot at solving that out. You should get negative 1,123. If we want to find out at which term number it's going to get to, oh, I messed up on this and didn't change it from years past. Change this to a big ol' negative 17,923. We don't know the n value at which term number, so we don't know n. Will it equal this? That's giving us a sub n. So let's plug that in for a sub n in our explicit formula and solve for n. Solve whichever way you like. I choose to move the constant over. Then divide by the number in front of the parentheses. And then add the 1 to get n is 430. So it'd be on the 430th term that it would reach that Mongo number. Zoom out for a moment and see if you need more time with any of those problems. And last thing we're going to do is we're going to take it and apply it to a word problem. Don't be scared. They're not too bad. Ethan averaged 123 total pins per game in this bowling league this season. He's taking bowling lessons and hopes to bring his average up by 8 pins each month. Write an explicit equation to represent the nth term of the sequence. So we're assuming that he's starting at an average of 123, and then he wants to add 8 each time. He wants to add 8 to his score each time, so we can assume that it's arithmetic. If we're going to write an explicit rule, remember with your explicit rule, you just need to find A1, and you need to find your common difference. Everything else will stay, like in this case, the blue ink. So we would have A sub n, any future score, is going to be his initial one, 123, plus the common difference, what he's adding each time, times n minus 1. We want to find out if that pattern continues of adding 8, after how many months will Ethan average 187 points per game? Think for a moment and see if we're plugging that in for a future term value, or are we plugging it in for n? N in this case represents the month number. It's like that's the month number after his lessons. A sub n represents his score after that many months. So in this case, they're giving us his score, so we're plugging that in for A sub n. So we have 187 equals 123 plus 8 times n minus 1, and we want to solve for n. You get 9 and go back and actually label it in the context of the problem. So it should be after 9 months. One thing I didn't ask you on here is like if you're using this equation and I say, what will his score be after 6 months? That would be an example of when you'd plug in a value for n instead of a sub n. All right, that's it, folks. Ask me questions if you've got them. I'd love to help you. Try out your homework once you finish these notes. Bye.